Hello everyone. The first class of special lecture on biopolymer science will begin. In this class, I will talk about the principles and equipment of infrared spectroscopy and Raman spectroscopy, and the structural analysis of biopolymers and synthetic polymers using those spectroscopy. Today, I would like to talk about the principles of infrared spectroscopy. First, let's start by explaining what spectroscopy is. Spectroscopy is a scientific method that examines the structure and physical properties of an object by observing the intensity of emission and absorption of electromagnetic waves as a function such as wavelength, frequency, and energy. It is classified according to the wavelength range of the electromagnetic waves detected and the physical quantities measured, absorption, emission, scattering, etc. It is widely applied from molecular structure analysis to astronomical observation. The absorption and emission of electromagnetic waves are based on the exchange of energy with atoms and molecules, and the spectrum corresponds to the transition between discrete energy states, energy levels, based on quantum mechanics. Spectroscopic methods measuring the absorption of electromagnetic waves include ultraviolet visible absorption spectroscopy and infrared absorption spectroscopy. Spectroscopic methods measuring emission include fluorescence and phosphorescence spectroscopy. Raman spectroscopy can be mentioned as a method measuring the scattering of electromagnetic waves. In spectroscopy, especially in measurements using electromagnetic fields in the region called light, a device called a spectrophotometer is used. This slide shows an example of a spectrophotometer that measures the absorption of light. Part of the light from the light source is absorbed by the sample, dispersed by the monochromator, and then the intensity of the light of a specific wavelength is measured by the detector. The result is generally expressed as a spectrum in which the horizontal axis represents wavelength and wave number and the vertical axis represents the measured physical quantity. By analyzing this spectrum, the structure and physical properties of the object can be investigated. Next, electromagnetic waves will be explained. Electromagnetic waves are waves that propagate changes in electric and magnetic fields. Electromagnetic waves move in space at a common speed called the speed of light. The speed of light in a vacuum is such a value. Electromagnetic waves are represented by characteristic values such as wavelength, wave number, frequency, and energy. Wavelength is defined as the distance from maximum to maximum. The wave number is the reciprocal of the wavelength and can be called the number of waves per unit length. The frequency of vibration is expressed as the number of vibrations per unit time. Electromagnetic energy is defined by the product of Planck's constant and frequency. Overall, electromagnetic waves cover a very wide range of frequencies, from 10 to the 5th power to 10 to the 21st power, and wavelengths from kilometers to picometers or less. The electromagnetic wave that can be sensed by the human eye is called visible light, but it is a very narrow range as a whole. The electromagnetic wave with a shorter wavelength than visible light is called ultraviolet, and that with a longer wavelength is called infrared. Infrared is further divided into three regions, called near infrared, mid-infrared, and far infrared. Infrared is 10 to the 12th power Hertz in terms of frequency, so it is in the region of terahertz, and in terms of wavelength, it is in the region of several microns. As will be explained in detail later, the energy of a molecule is divided into several layers, each of which has a region of electromagnetic waves having the same energy. Radio waves correspond to nuclear magnetism, microwaves correspond to rotational energy, infrared corresponds to vibrational energy, and visible and ultraviolet light correspond to electronic energy. Which of the characteristic values such as wavelength and wave number to use is roughly determined for each region of electromagnetic wave. Visible light, ultraviolet light, and X-rays are usually represented in nanometer wavelengths. On the other hand, radio waves are expressed by frequencies such as megahertz and gigahertz. Infrared light is represented by wave numbers in reciprocal centimeters. In the field of infrared spectroscopy and chemistry, this unit is sometimes read as Kaiser. Kaiser is named after a researcher named Heinrich Kaiser. However, this unit has not been used recently because it is not certified by the International System of Units. There is no other short and easy to read way to read it, so I will use Kaiser in this class. Next, let us consider the interaction between the energy of molecules and electromagnetic waves. The energy of a molecule can be expressed as the sum of the nuclear, electronic, vibrational, rotational, and translational components. Nuclear energy is a large amount of energy generated by the division or fusion of atomic nuclei. Electronic energy is the energy of electrons in an atom or molecule, and is determined by which atomic or molecular orbitals the electrons are in. Vibrational, rotational, and translational energy are related to molecular motion. Molecular vibrations are periodic displacements of the position of nuclei without movement of the center of gravity. The rotation of a molecule is the movement around its center of gravity. The translation of a molecule is the motion in which all the atoms that compose the molecule move at the same speed. The amount of energy becomes smaller as it goes from nuclear energy to translational energy. Each energy takes discrete values based on quantum mechanics and is called quantized. Since the energy of a molecule is quantized, it takes a discrete energy level from low energy to high energy. The lowest possible energy state is the ground state, and the higher energy states are the excited states, which are called the first excited state and the second excited state in order from the bottom. The change in the energy level by absorbing or emitting electromagnetic waves is called transition. When the energy difference between the N level and the M level matches the energy of the electromagnetic wave, that is, the product of Planck's constant and frequency, the electromagnetic wave may be absorbed by the molecule and a transition may occur. Conversely, electromagnetic waves can be emitted. When transitioning from a high energy level to a low energy level. This figure shows the relationship between electronic energy, vibrational energy, and rotational energy. The blue lines represent electronic energy levels, and a large amount of energy from ultraviolet or visible light is required to cause an electronic transition. The green lines represent vibrational energy levels, and a medium energy from infrared is required to cause a vibrational transition. The red lines represent rotational energy levels and a small energy from microwave satisfactorily cause a rotational transition.